Here's another splitting field example. This will give us another chance to run through our checklist of factoring techniques. The problem: let f of x be equal to x to the fourth minus 16x squared plus 4. I let k be the splitting field of f of x over the rationals inside the complex numbers. I want to find k and the automorphism group of k. In this case, if I want to find the roots of this polynomial, we only need the quadratic formula. So we let y be equal to x squared, we substitute, solve, then we put the x squared back in and take more square roots. So we see here that we have 4 distinct roots of this polynomial. Now, if we go to a calculator, okay, we check that we have 4 distinct real roots, and we can solve the problem with this. Now, you might not be comfortable working with a square root inside of a square root. It turns out in this case, we can do better. So our first root is going to be square root of 3 plus square root of 5. Our second root is going to be square root of 5 minus square root of 3. And that'll give us a much nicer answer to our problem. So the question is, how do we get to these roots? Now, rather than jump into that, let's run through some items that we have in our checklist. So I have polynomial with rational coefficients. First thing we check, rational roots test. So in this case, possible rational roots are going to be plus minus 1, plus minus 2, plus minus 4. And if we check all of those, okay, none of them are going to be roots. So we've ruled out any rational roots in this case. Now, that doesn't mean that this polynomial is irreducible, because it can factor into, okay, a pair of quadratics that are irreducible. Next, we note our function is even. So if I replace x with minus x, we get the same polynomial back. That means if I could find any root alpha, then minus alpha will also be a root. Next, I take the derivative, and then we take the greatest common divisor of our function with the derivative. So this is our test for multiple roots. If we have a multiple root, then this greatest common divisor is not going to be equal to 1. Now, if we take the derivative, okay, we get 4x cubed minus 32x. We factor, I get 4x times x squared minus 8. And we note x squared minus 8 does not divide our function, so the greatest common divisor is equal to 1. So no multiple roots in this case. Finally, okay, we put this together. The roots are going to be, okay, they're distinct. So we have plus minus r1, plus minus r2. I'll choose r1 greater than r2, and both of these will be positive. Now you'll note with the solution we've already found, okay, all of these properties check out. By design, this problem's too straightforward. Other techniques we can bring in to control the behavior of the roots. We can just graph the function, so that brings in calculus and technology. In our case, our picture looks like this. We see that we have 4 real roots. If we didn't have technology, okay, we can use the end behavior of the polynomial and the bisection method to try to isolate the roots and regions. So for instance, if we took our polynomial, evaluated 0 and 1, we get 4 minus 11. So there's a sign change. We know by the intermediate value theorem that we have to have a root between 0 and 1. Likewise for 3 and 4. Then we also have Descartes' rule of signs. Now, getting back to our problem, we have control over our roots. So we'll take our polynomial and then just write it as product of linear factors. Now when we simplify, we get 2 equations. We note for r1 squared, r2 squared equal to 4, r1 and r2 are both positive, so I have that r1 times r2 is equal to 2. Now with this, I'll take r1 plus r2, r1 minus r2, square both of them. We substitute, and I get r1 plus r2 is equal to 2 square root of 5. r1 minus r2 is equal to 2 square root of 3. So when we solve for r1 and r2, we get the roots of our polynomial in the form that we had before. To answer the original problem, we want the splitting field of our polynomial over the rationals. It's going to be the smallest subfield of complex numbers that contains all roots of the polynomial. So we take the rationals, we join all of our roots. Here we need only the positive roots. And we can clean this up to get q adjoint square root of 3, square root of 5. So that's our splitting field. Now, we note the degree of k over the rationals is equal to 4. If I consider q adjoint square root of 3 plus square root of 5, okay, let's find the degree of this subfield over the rationals. I have 1 square root of 3 plus square root of 5. Okay, we square this. I get 8 plus 2 square root of 15. We see that this is a linearly independent set, so the degree of this field over the rationals must also be equal to 4. That means these two fields are equal. And we also have that f is the minimal polynomial of square root of 3 plus square root of 5 over the rationals. So it must be irreducible over the rationals. For the automorphism group of k, this is going to be isomorphic to a product of z mod 2 with itself. Now, representing k as q adjoint square root of 3 square root of 5, we see that all automorphisms are given in the form, okay, sign changes of square root of 3 and square root of 5. So there are 4 of these, and they all have order 2. So that means z mod 2 crosses z mod 2. Now, let's check one more property. So we have that if alpha is a root of the polynomial with rational coefficients, we pick an automorphism phi of q adjoint alpha, then phi of alpha is also a root of f. So in our case, if I let alpha be equal to square root of 3 plus square root of 5, if we apply each automorphism, then what we'll get is, okay, our roots as we noted before. So all sign changes on square root of 3 and square root of 5.